Okay, this is hopefully a review for you from pre-calculus, but I know that that's been a long time ago, and so it's fine if it's not. So I'm going to try to not give you more information than you need and not try to be too windy, but just know that some of this hopefully is something you already know. So we're talking about logs today, and if you remember much about logs, they're basically the inverse of the exponential function. And so if you look at this first part of it, it says e to the x is 1 to 1, and so it has to have an inverse. But if we switch x and y in that equation, then we get x equals e to the y, and we really don't know how to solve for that. We really don't, up until now, have the tools to figure out what that actually is. So we have to define a new function to undo e, or undo all of these exponents. And so that's where the natural log and the log functions came into play. Is they said, okay, here's this function, e to the x, and we want to figure out what its inverse is. And so we defined this thing called a log, and in e's case, since it's the natural base, we call its log the natural log. We write it like this, ln. It's really just log base e. It's log base e, but because we use it so much, we gave it its own symbol, which is ln of x. So the natural log is the inverse of e, so they undo each other. Just like, so if we have 10 to the x, the inverse of that would be log base 10. And if you remember things from your log stuff, log base 10 is the only one we can write without writing the base. We can just write it as log. Anything else we'd have to write the base. So if we had something like 2 to the x, I tripped you up by doing it on the other side, right? Okay, 2 to the x, the inverse of that is log base 2. It's not wanting to write on me. Log base 2. That is beautiful. Log base 2. It's the inverse. Okay, so let's talk about the graphs of them first. You actually can see the graphs right there of e to the x and ln of x. So remember, the domain of the log function is, you know what, let's start here. Let's start with e to the x. Okay, if the ln is the inverse of e to the x, that means we would switch their x's and y's, and we would switch their domains and ranges, right? So the domain of e to the x, what numbers can we put into e to the x? Well, the domain is all reals, because I can put any number in there and get out a value, right? Because it doesn't matter. I can put in negative numbers, I can put in fractions, I can put in whatever I want. It still will spit out a value. And then the range, let's think about, when I put in 1 or 2 or 3, I get out a positive number, right? And when I put in -1 and -2, I still get out a positive number, right? Because e to the -1 is just 1 over e. E to the -2 is 1 over e squared. So I still get out positive numbers. So my range for e to the x is that y is greater than or equal to 0. And sorry, not equal to, just greater than, because if you think about this graph right here, it'll take a second to update, but there it is. Okay, so if you think about this graph, we look and see that it never actually touches 0. Remember, there's an asymptote right here. So it approaches 0, but it never touches it because there's not a single number we could put in there that would make it equal to 0. Okay, so that's the domain and range of e to the x. And since ln is the inverse, that means we switch the x and y, and we also switch their domains and ranges. So our domain is now y has to be x has to be greater than 0, and the range is all real numbers. I got ahead of myself and I tried to write it too fast. There we go, all real numbers. So the idea is the log function, or the natural log, either one, they're going to look very similar, are going to look more like this purple function up here, where the range can take on any real value. There's any value that can come out, but we cannot put negative numbers in there because e to the x can never output negative numbers. And since the output of e to the x is the input of ln of x, it can never input negative numbers. So I hope that was sufficiently confusing. I hope it actually wasn't, but think about the output of e to the x is the input of ln of x, and that's how I remember which one is which when I'm looking at graphs. So let's, with the calculator, we're going to use our calculator to graph ln of x and log of x. So go ahead and do that on your graphing calculator. I'm just going to sketch it because it's not, well, I do have one here, actually. Let's see if it will come up. There you go. Okay. There's log and ln. So the log is the red one, and the ln is the green one. And so let's just kind of think about this a little bit logically and think about why they work this way. If you think about that, the ln of x, or let's say log of x, is the inverse of 10 to the x, right? And so basically we're saying 10 to the what equals y. That's kind of what we're thinking. So what I think of first is I think of, well, what does the graph of 10 to the x look like? Well, when I put in 0, I get out 1. When I put in 1, I get out 10. When I put in 2, I get out 100. When I put in negative 1, I get out 1/10. And then when I put in negative 2, I get out 1/100. So the graph of the natural log, not the natural log, of log base 10, I would switch all of my x and y's, right? So now, when I put in 1, I'm going to get out 0. When I put in 10, I'm going to get out 1. When I put in 100, I'm going to get out 2. When I put in 1/10, I'm going to get out negative 1. And when I put in 1/100, I'm going to get out 2. So we can look at this graph and see if that follows the pattern. Okay, when I put in 1, I get out 0. Well, that makes the most sense, right? And then when I put in 10, which is way over here, I get out 2. Yep, that works there. Then when I put in, obviously we're not going to put in 100, but when I put in 1/10, which is, say, right here, when I put in 1/10, I get out negative 1. So that's right there. Right there. And then when I put in 1/100th, I get out negative 2, and you see it's approaching that asymptote right there at x equals 0. So let's look at the natural log and see if this works the same. Okay, so the natural log is the inverse of e to the x, correct? Yes, Mrs. Barney, it is. Okay. E to the x. So let's look at e to the x, okay? X's and y's. When I put in 0, I get out 1, just like every other exponential. When you put 0 in, you get out 1 because anything to the 0 is 1, okay? When I put in 1, I get out about 2.7, and when I put in 2, I get out about 7.3. I had to do that on my calculator before because I could not remember. And when I put in negative 1, I get about 0.36, and when I put in negative 2, I get out 0.135. So let's see, the graph of ln of x should be the inverse of that, meaning we just switch the x and y values, right? So when I put in 1, I should get out 0. When I put in 2.7, I should get out 1. When I put in 7.3, I should get out 2. And when I put in 0.36, I should get out negative 1. When I put in 0.35, I should get out negative 2. Okay, so let's look at our graph, make sure it follows that. Put in 1, get out 0, put in 2.7, I get out 1, that is right about, let's see, right about there. Put in 7.3, I get out 2, yep, right about there. And when I put in negative 1, I get out 0.36. That's right about there. And so you just see that, again, it's still approaching the asymptote of x equals 0. All of these logs are going to have an asymptote at x equals 0 unless they're shifted. And see that they all share a common point. They share this common point right here. This point that because anything to the 1, or excuse me, anything to the 0 is 1, log of 1 will always equal 0. It doesn't matter what base we have. ln of 1 is going to equal 0. Log base 2 of 1 is going to equal 0. Any log of 1 equals 0 because we're saying what 2 to the 0 equals what? It equals 1. Okay, so those are inverses of each other. So now that you're confused, let's go back to some actual practice problems. Pull them back up here. Okay, so we have those graphs, and similarities, remember, we're going to have that same point. We're going to have that point 1, 0 on all of our log graphs. Okay? So without a calculator, can we sketch the graph of ln of x minus 2, absolute value of all of that? Okay, so first things first, let's sketch, I'm just going to do it in like a lighter color. We're going to sketch the graph of ln of x. Okay, so it crosses there, has an asymptote there, and when x equals 2, y equals 1, so it's like, okay, that's the sketch of ln of x, correct? Okay, so this tells us that it's going to shift to the right 2. Oh, and we're going to remember that our original graph had an asymptote here. So we're going to shift to the right 2, because that 2 is inside the function with the x, so we shift right 2. And then the absolute value is around the entire function. Do you see how this absolute value is affecting everything? It's affecting our outputs, not just affecting the x's. So that means it takes all of our y values and it makes them positive. So these y values right here, instead of coming down like this, they're going to go up like that. They're going to be positive numbers. So on this side, it's still going to do the same pattern, right? But then this one is going to go up like, it's going to go like that, because we just reflected it over the x-axis. And remember, since our asymptote was at 0, our new asymptote is at 2, because we just shifted everything over 2. So our new asymptote is at x equals 2.